Okay, so now we're recording. So we are today on the 7th, and we'll start in on lecture 4A, still part of the Pep8, Warford book, Pep8 computer, virtual machine, not a real computer. And so now we're going to start in on computer architecture. Last class we worked on numbers and so forth, as well as looking at arithmetic, shift left and shift right and so forth and so on. But before we do this, I did open up, hang on a second here. Review, yes. So I'd like just to review, these are 3 questions that I randomly picked out of the homework. So this isn't the homework number or anything, but anyway, there's 3 of them. There's one there, there's one down here, and so forth and so on. So here's the first one, just to review then. This is just adding and also showing the effects on the status flags. Remember that Pep8 has 4 status flags. Well, yeah, 4 status flags. In a real CPU, there's more than 4, but we're going to just study 4. This is the sign bit, or you call it a bit or a flag. It's just 1 bit. And in is determines whether it's a positive or negative number. And so it's always the most significant bit. If we're looking at an 8 bits, then the most significant bit is that. If you were looking at 32 bits or something, just making this up, doesn't matter, then that's the most significant bit. Here, now we have another person. Anyway, so that's what this is. And so so when you do an add operation, the bits, the flags set or unset. Set means it goes to 1. 0 means it's not set. And so the flags set and unset based on the operation. They do it automatically. It's hardware. The electricity just flows right to the bits. So when the result, after the result, I'll put it that way, if it's 0, then the sign bit is 0. If this is a 1, it's a 1. But see, in this case here, we add these together. I won't go through the whole add, but we get to here, 1 plus 1 is 0, carry a 1. So there's actually another 1 out here, so to speak. But whenever we're working with registers, whether we're working with 1 byte or 2 bytes or whatever size of register that we're working with, then that's all the space there is. So if it overflows or carries out, like it does in this case, this is the actual answer, and this is just something that carried out of it. But what will be saved will be just this. That's the adding of these 2 numbers. So in this case, the sign bit is 0 because it doesn't count that one. See, it's just counting that one, and 0 means positive. Okay, so sign bit's it's a positive number. I'll put it that way. The 0 flag, this is not 0. So it doesn't set. If it were all zeros, 8 zeros right here, forget this one. That one doesn't really matter. If there were 8 zeros right here, then the 0 flag would set to 1. And then remember that if there's some kind of an operation, whether it's whatever the operation is, if it carries out like I just had there, let me just hit the undo button like that. If it's 1 plus 1 is 0, carry a 1, then both the V flag and this stands for overflow. The overflow flag sets and the carry flag sets. And if the carry flag is used with unsigned integers, and the overflow flag is used with signed integers. So it depends on what this is. So if these are signed integers, signed meaning they can be negative numbers or positive numbers. If that's the case, then the overflow flag would set because it works with signed integers, and it does. And if that's the case, if these are signed, the V flag sets, but so does the carry flag. But the carry flag is sort of impertinent to signed integers. So even though the carry flag sets, it's just the way it works. It would never be checked. It sets to 1, but carry is only used with unsigned. So it would never be checked with signed. But the V flag would, the overflow flag would be. On the other hand, if these are 2 numbers that are positive numbers only, no negative numbers, either 0 or positive, and we add them, if it carries out, then the carry flag sets as it has right here, And the V flag does too, but now the V flag would never be looked at by the CPU, or I say looked at, doesn't get looked at, but would not be, it's impertinent, it's irrelevant. It doesn't, it just sets automatically, because this is all hardware, it's just circuitry. And so if it carries out, the V and the carry flag are both going to set, but only one of them will be pertinent to the particular operation, whether it's signed or unsigned. So that's that. Okay. Okay, guess that's probably it. We'll go to the next one. We're just doing 3 of them here, just as a little review from last class, that one, and then one more down here. And then we'll get into lecture 4A. What's wrong one? Okay, convert the following decimal signed integers. So these are signed now to binary. So convert that to binary. Show the effect of the arithmetic shift left operation on it, and then convert it back to decimal. Okay, so it's a -1. So convert it to binary. I did it off to the side here. Here's a -1. Here's remember when these are signed. So this is a negative number. So we have to first get the absolute value of the number 1. This is 2's complement, right? 2's complement. So here's a 1. Then we flip all the bits. If it's a 0, make it a 1. If it's a 1, make it a 0. So we flip the bits and add 1. And so 0 plus 1 is 1. Oops. And then all the rest of the ones just carry down. So that's a -1, because this is a 1. And if we want to find what a -1 is, we do 2's complement. And now we have a -1. Okay. And then after we have the -1, shift the bits left. So this one here shifts out, shifts to the left, it's gone. And all these other 7 1s move to the left, 1 position. Here they are. And then if you look in the notes, there's always a 0 put in at the least significant bit right here, the one on the right. Shift the bits to the left and put a 0 at the beginning. And remember what that does? It doubles the value. Okay. So if it's -1, now it's a -2. Now, why do we know that's a -2? I did it right here. Here it is. Here it is right here. So what is that? Well, let's do 2's complement on it. Shift, flip the bits, add 1 to it, and we get this. And what is that? That's a 2. Whenever we do 2's complement, it gives us the absolute value of the number. Okay. Assuming it's a negative number to begin with. And by the way, we know it's negative because it's a 1 right there, right? That's the sign bit. Okay. See here's let's see what would be an example here. Well, here's a 1 right here. And you can see it's a +1 because it's a 0 there. Anyway, so we know that's a negative number. So what is it? Well, we'll do 2's complement. Flip the bits, add 1 to it. And now we have the absolute value, the positive of whatever this is. And what is it? It's a 2. So that means this is -2. Okay. We'll do one more. All right. Again, this was a homework assignment. These were all, I took them out of the homework at different spots, but assuming 8-bit 2's complement binary representation. So in other words, it's already in 2's complement. So we can see it's got to be a negative number. Oh, wait. Oh, this is what we're given right here. I'm sorry. We're given this, but we know that's a negative number. And I'd like to make this point. I didn't during our last lecture. Here, I'll do it in 4. Remember that every hex digit, that's hex 0, is, we can represent it in 4 bits. Oh, I don't really want to do that. Hold on a second. Undo. There. Okay. I'm using Microsoft Word, so it indents automatically. Here's a 1. And so that's that. Here's a 2. So these are hex. They're decimal too, of course, but they're hex up till when it gets to 10, then hex is an F, and there is no 10 in decimal for a single digit. Let's do this for a second. Go like that. Okay. So I'm just going to do it like this. Oops. that. I'm sorry to put a 10 down there. Whoops, come on, Dennis. There we go. I'm just gonna do this because I get myself confused. And I still did, didn't I? Okay, that's right. There we go. Oh, I see what you did. There we go, like that. Okay. Okay. The reason why I wanted to show you this was that when we see a hex number, hex value, I guess, we can tell automatically that it has to be that it's got to be a negative number. I mean, assuming it's a signed integer. I mean, it can be negative or positive. We can see right away that a B4 is a negative number because everything starting with 8 and down, the most significant bit is a 1. And if the most significant bit's a 1, it's a negative number. And so everything from 0 to 7, the most significant bit is a 0. So we know automatically that's a negative number. Okay. And so if we convert B4, there's the B right there. We can see right here, 1 0 1 1. And then a 4 is 0 1 0 0. That's right here. And okay, so then we do 2's complement on it. And so we flip the bits. There's a 1 there, so now it's a 0. There's a 0 there, so now it's a 1, and so forth and so on. So flip the bits, add 1 to it. 1 plus 1 is 0, carry a 1. 1 plus 1 is 0, carry a 1. So we get a 1 right there, and a 1. And this remains the same. Okay. And so then we can see what that is. 1, 2, 4, 8. So we have a 4 and 8. That's 12. Okay, and here's a 64. This is 8 plus 4 is 12. Plus 64 is 76. But this is not 76. This is 76 after we did 2's complement on it. So that means that the original B4 is negative 76. This is a negative number. So we use 2's complement to find the positive number. And that tells us it's a 76. So therefore, this is a negative 76. That's how it works. If we had something like, I'll keep it simple, 23, a hex 23. Well, we know that that would be, so be a 2 3, be 0 0 1 0. That's a 2, and then 0 0. Oops, yeah, 1 1. That's a 3. So what is that? Well, it's 23. We know that. So then if we did, but see, we can see it's a positive number automatically. So we don't really need to do 2's complement on it. It's a 23. It's done. We know what it is. On the other hand, and it wouldn't matter. Let's make it 2F. It doesn't matter what it is. See, it's a 2. It's a positive number. Okay. So anyway, that's just showing you that whenever you see a hex value, all you have to do is look at the first digit, and if it's 8 or more, see, that's where the 1 starts right there. Everything below 8, see, 7 is the largest you can go with 3 digits. And if you go to an 8, you go to that 4th digit right here. Anyway, that's that. So we'll call that a wrap. I just wanted to go over that a little bit. Let's see. Okay, sure, why not? And so again, we're going to start in on lecture 4, 4A in the Warford book. And that's just right here. And so just a quick reminder then, the Warford book, Warford is the author, and he is I assume he's still there, I don't know, a professor at Pepperdine University over in the coast up north of Santa Monica, north of Malibu. A fantastic campus overlooking the ocean. Anyway, he wrote the book and developed this Pep8 computer, and the book describes a computer by levels. And so now we're going down to the 4th level. I didn't actually put that in the notes here, but some of the notes previously, we didn't actually do the application level at the very top. It's just the applications that you use, the programs you use. we started at the high level language in lecture, what was that, lecture 2, where high level languages, we did some C++ and looked at the runtime stack and so forth. And then we went into numbers representation, but now we're going to go down to here, I'm spacing out here. It doesn't really see there. It's actually the ISO level, I believe, instruction set architecture level. Well, I'll just put it this way. It doesn't matter what it's called. What we're going to do then is take a look at a CPU and the key features of a CPU, the control unit, the registers, the little microchip itself. Every computer has some kind of a processor. And so we'll look at the registers and how it deals and works with RAM and so forth and so on. The flags, these are the registers right here. So that's what we'll start with. This was an original note here, just talking about how the CPU has to fetch an instruction from RAM. Fetch means to get it. But remember, the CPU does not work with input devices like keyboard or mouse or anything like that directly. And the CPU cannot work with output devices like the screen or writing it to a file. The CPU gets all of its instructions from main memory, RAM. And then when it processes an instruction, the results are stored back in RAM. If something's going to be sent to an output device, the CPU sends a signal on the bus. That's the electronic pathway, so to speak, a signal that tells RAM to go to a particular location and get something and copy it on the bus and send it out to show it on the screen, display it on the screen or whatever. Likewise, if somebody types something in, it goes on the bus and goes into memory, into RAM. And then the CPU can then send a signal and say, get that thing at some memory location, put it on the bus, copy it, just a copy of it, still there, and bring it into the CPU. So CPU and RAM work together at lightning speed, at the speed of electricity, no moving parts. And so that's kind of, this is just, says Pep8 has no hardware. Instead, the Pep8 is software and simulates 2 input types, keyboard and text file, and 2 output types, console, that's, keyboard. Output, that'd be the screen and text file. However, in a given program, only one input, this is talking about the Pep8, that you can only do one thing at a time with Pep8, but we're not going to get that deeply into it. We're just mostly looking at the fundamentals and the principles of how a computer works by using Pep8. And the reason why Warford uses or came up with this idea of using this virtual machine is that there are thousands of CPUs, and every CPU is very specific. It has its own instruction set. It has its own set of registers, and they vary. I mean, there's a processor in a fuel system in a car. There's a processor in a cell phone. There's a processor in the computer in front of you. So there's thousands of them, but they have certain things in common. And so that's what the author has done is taken the things that are the fundamental principles of how a CPU works with a program to execute it. Okay, so that's what we're going to do. That's where we're at. And so in this Pep8 computer, then these are registers here. CPU contains 6 specialized memory locations called registers. They're in the chip itself. It's kind of sketchy to say memory because usually we think of memory as RAM, but in this case we're talking about on the little processor, the little CPU chip itself, central processing unit, CPU. There are these registers. And the Pep8 computer is only a 16-bit computer. Originally, back in about 1988, I had a DOS operating system, and it was only 8 bits. I think it was 8 bits. I don't know. I think so. Yeah, pretty sure. And then they came out with 16 bits. Well, actually, it may have been a 16-bit. I don't know. Who knows? I didn't do much with it because I didn't know what I was doing. Did some things, though. And then in about 1993, I bought my first Windows operating system, and it was a 16-bit. That was 1993. And it was the best you could buy. Well, not the best, but I mean, it was a really nice computer. And I spent $3,500 on it in 1993. That'd be like $10,000 today. Anyway, So that tells you kind of where this is at. A 16-bit computer is really like in the mid 90s, something like that. But now, of course, I don't know what it was, probably about 1995, they came out with a 32-bit processor and Windows 95 in 95, and that was a 32-bit processor. And so the more bits, the more the CPU can process with every clock tick. Each processor has a system clock, but it's not a clock on the wall. It's a little it's circuitry that emits pulses of electricity at very precise intervals. And the electricity is a very small amount. It might be like 5 volts, very small amount. And with each pulse, the electricity flows through the millions of circuits. And so the larger what we call the word size of the CPU, like in other words, 16-bit is the word size. A 16-bit computer, they say the word size is 16-bit. That's just what they call it. A 32-bit computer has a word size of 32 bits. And then in 2005 or 2005, something like that, 2000 probably, they came out with a 64-bit processor. Now I'm talking about for PCs. They may have had processors prior to that, but popular to where you or I could go out to a store and buy a 64-bit processor with Windows on it or something. And that was about 2005. So it's gone from the 1980s, maybe 1978, 8 bits, to the 1980s, 16 bits, and into the 90s, and then early 90s, mid 90s, 32 bits, and then 2003, 64 bits. Okay, and so as the word size has gotten larger, the computer I have is a 64-bit, so the word size is 64 bits. As it's gotten bigger, it can, with each clock tick, then 64 bits get processed at one time. In the old days, when it was a clock tick, 8 bits would be processed. And bits are the whole thing. It's all information and instructions, and it's the music you listen to, it's the things you transmit or send in an email or a video that you're watching. So the more bits that can be processed at any given with each clock tick, the more powerful the machine. It's called throughput, by the way. Oops, doing it in caps here. I'm not going to ask this. I thought you might want to know this because you'll get it when you get to the university. Throughput is just a term that means the actual amount of work that the computer can accomplish. So there we go. So more throughput when with a larger word size. Anyway, now where we are though, the author has created a Pep8 CPU, and the word size is 16 bits, which means that most things get processed in 16-bit chunks. It's a little sketchy how he has done it. I think maybe it's something I just don't know. I'm really not sure. But like here, for example, there's a register that has 4 bits, and I think that's odd. I think there would always be at the minimum a bite-sized chunk, 8 bits or something. Okay, so 4 bits is kind of odd. It's something to be processed. And the other thing that's odd about it is this particular register here is actually 3 bytes, 24 bits. See, there's 1, 2, right to there, and then 3. So this is a 24-bit register. So I think that's kind of odd that one register is 4 bits, but the majority of them, what we call the accumulator, the index, the PC, program counter, and stack pointer, these are all 16 bits. And that would be more typical of a 16-bit computer. And so if it's a 32-bit computer, the accumulator would be 32 bits, the index register 32 bits, et cetera, et cetera. If it's 64 bits, then these, what we call general purpose registers, accumulator, index, program counter, stack, they would all be 64 bits. So it depends on the word size of the computer. If the computer is 64 bits, then the main registers will all be 64 bits. And I just don't know myself. I don't have any experience in that area. I guess I'm just too lazy to ever look it up, whether modern real CPUs, say for a 64-bit computer, whether some of them are smaller registers. Probably they are. I mean, I suspect this is actually not totally unrealistic right here, because I don't think on a 64-bit computer that there'd be a need for a 64-bit flags register. This is the flags register. In the flags register, each one of these bits, these are individual bits, each bit, they have, it's like each one has a separate wire going to it, so to speak. They're just circuitry. But like when we've already talked about that, if you add two numbers and the result is 0, then the 0 bit's going to flip to 1, and the other bits will not be affected. So it's just a register that has 4 individual bits, and each bit is independent of the others. In this register, the accumulator and the index and PC and stack pointer, they all act as one. In other words, when you put something into the some number into the accumulator register, it's going to take all 16 bits in there, to do it. In other words, the computer doesn't look at individual bits, so to speak. But the flags register, it does. It'll see if the 0 flag sets to 1. That would tell the computer then that the result was a 0. Okay. Just as a side note, real quickly here, if we go back to C++ for a moment, if you do something like this, say you have something like this. I'm using Microsoft Word, so it's capitalizing things. Okay, it's bugging me. I got to change it just for a quick sec here. What else do we have there? Okay, so this would be most modern languages, C++, Java, etc. So here we have two variables, and it's comparing them. If num1, like number 1, equals number 2, okay, see how they're equal, else they're not equal. Okay, so how the computer compares two numbers or two letters and so forth, it does it by subtraction. So it subtracts 3 minus 3. Yeah, we'll leave it at that. It just subtracts the numbers. It actually uses the ASCII values, but it doesn't matter. The point is it subtracts 3. 3 minus 3 is 0. So if it does this right here, all it would have to do is see if it subtracts them, it could immediately send a signal to the 0 flag, that 0 flag register, and if it's a 1 there, they're equal. If it's a 0, they're not equal. So see, it makes it so that it can be done in nanoseconds. It's just that register, that the 0 flag, it just it can check that immediately and know immediately at the speed of electricity whether the numbers are the same, whether the two values are equal to each other. Well, okay, so there are some really nice techniques that that are built into the CPU and into the instruction set and into the registers for processing quickly. In other words, when over the years, as computer scientists have developed these processors and these languages and so forth, they want to avoid having to do any kind of interpretation. Interpretation requires software. Whenever you get software involved, it takes more processing steps to come up with an answer. If you've got something that's hardware so that it does these things and a 1 automatically goes into that, just electricity flows and it's a 1, it's super fast. But there's a lot of things like that, which we'll kind of study a few of those things. So anyway, these are the registers. The first ones are just where the status flags are, and they simply reflect whatever operation just occurred on them, whether it be adding or anding, or how we did and or, exclusive or, subtract, stuff like that. these flags set constantly. If there's an overflow, the V flag sets like that. And then we have a couple of what we call general purpose registers, the accumulator and the index register. And we'll use the letters A and X for accumulator and index. I'll just say CPUs for PC computers, Intel processors. If you go to go buy a new computer, it's going to have a CPU and so forth, whether it be Intel or AMD or whoever it is. There's always an accumulator register and an index register. Okay, so Warford, the author, has just taken. By the way, they might have slightly different names, but still, there's always an accumulator and an index. In MASM, Microsoft Assembly Language, which the second half of our semester we'll be writing assembly language code. And in assembly language, everyone studies a particular language that is pertinent to a particular processor. In other words, if you're going to do something for a fuel system on a car, if you work for an auto manufacturer, then the chip that's in that fuel system would have a very specific instruction set, and it would have its own language that you would write code in assembly language to program that fuel system. So I don't know if there's an accumulator and an index register with robotic stuff, but for PCs, servers, things like that, where we're using either Linux or a Mac or a Windows machine or whatever, there's always going to be an accumulator and an index. In MASM, well, let me put it this way: in a CPU, like an Intel processor that's used for Microsoft Windows, the accumulator used to be called accumulator A. That's oftentimes what they would do. And then that was way back when it was 8 bits. Hold on. Yeah. And then when it was 16 bits, they called it the AX register, 16 bits. And then when they went to 32 bits, am I telling you correctly? Yeah. They went to EAX. So this is 8 bits. That's back in the old days. The accumulator register was 8 bits. Then they went to 16 bits. Then they went to 32 bits. And I forgot what the 64-bit is, but it's a different name again. We don't really care, right? The point is the author is just calling it A. But there's an accumulator, no matter whether they call it A or AX or EAX. There is. So we'll leave that alone. And then there's also an index register. And we'll talk more about that in a minute. And then there's something called a program counter, which we'll talk about that. The program counter is, these first two, by the way, the accumulator and the index register are the general purpose registers used for math operations, subtracting, adding, shifting the bits left, shifting the bits right. Typically, for example, you would write an assembly language instruction and you would say, move to the accumulator 7. And then that's just an assembly language instruction. I'll keep it simple. It'll be move to the accumulator. We'll just keep it simple, 2. Okay, and then the next instruction would be now in the accumulator there'd be a 2. It's a 16-bit accumulator. So let's do it over here. 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So there's 16 bits, and that's a 2. Okay. And then arithmetic shift left, accumulator. Arithmetic shift left. These are actual assembly language instructions. So first you have to put it in there. You got to put it in the accumulator, and then shift the bits left. Now, if you shift the bits left, that means there'll be a 0 put right here, and this 0 is gone. And so what's that? That's a 4. So remember, whenever you shift bits left, it doubles the value. So this is typical assembly language and showing how it works. And so the point there is that the accumulator is the workhorse. It's the register that we we first put something in it, then we add something to it, then we subtract from it, and then we shift the bits and whatever. That we use the accumulator. We can also use the index register. It's a general purpose register, but the program counter is different. The program counter is pretty much off limits for programmers. We can't really do much with the program counter because it's the specific register that keeps track. It holds the memory address of the next instruction to be fetched by the CPU. Hang on 1 second here. Oh, set that one wrong. Oh, I don't want that one. This one. I didn't think about loading this. I could have loaded this into our today's lecture. Ah, okay. Hang on, bear with me just a second here. Yeah. Okay, so yeah, all right. We talked about the stack. We did talk about the stack. Good. So we kind of, or hopefully you guys remember that. So here's a C++ program. In fact, I may even have used this code. The more I think about it. Anyway, so here's a program, and of course this gets compiled by the compiler down into this. Okay, and so we're pretending like this program, we're just sort of jumping ahead to this point right here where this function call is. So the whole program, all of this gets compiled into thousands or millions of instructions, all in Pep8. See, it would be in 16-bit instructions, 16 bits. Okay, in a 32-bit computer, then each one of these it'd be compiled into 32-bit instructions. And I think that's what I did here. Like here's the get number. Here's the get num function, and it's been compiled from that into 32 bits, 4 bytes. By the way, this is not actual code. I faked it on the ones and zeros. I mean, the C++ is correct, but here's the function call, and it's going to jump down to here. And right at this function call, that's at memory location 5,000. I just made up these addresses. That's a very small number. It could easily be 2 billion. Okay, but anyway, here's the instruction. And it's not going to, normally it does everything in sequence. It would do this instruction, then it would do this instruction, then it would do this instruction, like that. But it's not, because whenever there's a function call, it has to jump down to the function code, which is right here. I did it in red to match it. Okay, there's the function, get num function. And that's at location 5024. That's the memory address. This instruction is at 5,000. Well, plus 5,001, 2, 3, but it's the first, the address of the first byte is the important one. That's the one the computer needs to know, because it knows how to find the other, in this case, they're 4 bytes each, so it knows how to find the other 3 as long as it can find the first one. So it's at this location here, and it fetches the instruction. It goes to memory. Remember, the CPU fetches an instruction, then it decodes the instruction. That means and we're going to learn how to do that today. Even it decodes the instruction, meaning it figures out what to do. Then it does it. It executes. So fetch, decode, execute. And then sometimes books will say there's a 4th part of the cycle, which is to store the result. So, but anyway, fetch, decode, execute, fetch, decode, execute, millions of times per second. The clock tick is ticking at 2 gigahertz, 2 billion cycles per second. Okay, so it starts right here. And so what it does, there's a PC. Here's the PC. That we talked about that. Oops. No, not that one. Hang on. Here's the PC register, program counter. It holds the memory address of the next instruction to be fetched. That's an important point. Not just a quiz. I mean, it's sort of fundamental to how this whole thing works. The program counter holds the memory address in RAM. RAM is memory of the next instruction to be fetched. Okay, so in the PC is 5,000. 5,000. Okay, and so the CPU looks to the PC and sees that the instruction is in memory at 5,000, the address 5,000. So it sends a signal on the bus to memory to go to location 5,000 and maybe make a copy of that instruction. And so it goes to 5,000. Now, again, this is a 32-bit instruction, a Pep8 16, but for right now, we'll go 32. So it goes to 5,000, and it knows it's 4 bytes, 32 bits. So it gets that whole instruction, puts it on the bus, and brings it into the CPU. And when it brings it into the CPU, it puts it into the IR, instruction register, right here. Now, in Pep8, the instructions can either be 1 byte or 3 bytes. That's a little odd. Normally, I would say usually instructions are, if it's a 32-bit computer, they'd be 4 bytes. Okay, but they might have some that are less. I don't know for sure. Might be some that are 1 byte, but just think of it as each instruction is 4 bytes. So it goes to it sends a signal to RAM to put on the bus instruction at location 5,000. It brings the instruction into the CPU and puts it into the IR register. See, it has to put it somewhere. It can't just, I don't know, let it float around or something. It has to be put on the bus, electronically brought in, and it's automatically, boom, it's put into the register. That's the fetch. The CPU has to fetch the instruction. Then it has to decode it. It has to look at the first byte. That's a special byte. It's the instruction specifier. The instruction specifier specifies what this whole thing is, what the CPU should do. It doesn't have to look at all of them initially. It has to look at at just this. That's the instruction specifier, and it sees what that is. Maybe it's add something or shift the bits or something. So that's the second one. Fetch it from RAM into the CPU, then look at the first byte and decode it, and then execute. So fetch, decode, execute, and then then fetch the next one. So when it fetches this right here at location 5,000, this has to change. That's to get this. So the CPU goes, okay, I'll go there and I'll get it. So then what it does is it increments by 4 because the instructions are all 4 bytes each, because this is the next instruction. Okay, so it puts 5,004 here. So it does that, it fetches the instruction, and then it increments the PC to 5,004, but it's still working on this first one. So then it decodes it, and when it decodes it, it says, oh, it's a function call. Jump to the code, the get num function. That's it. Once it fetches it in, then it decodes it and sees, oh, this is a function call. If it was not a function call, it was just to add numbers or do something else, then this would be the next instruction. That's the very next one in line. Okay. But in this case, it's saying, no, don't do that. Jump to this function. This function is down here at location 5,024. Okay. So it takes this 5,004, which is presently in the PC, that's this right here, and it puts that on the runtime stack. It saves it there. It's like putting it on a shelf. It's going to come back to it later. It puts that on the runtime stack. Okay, and then what it does, it loads 5024 into the PC. Like that. This one is saved. And so it fetched this in, realizes it's a function call, checks the PC. This happens automatically, by the way. It's just all hardware. Checks the PC, and the next instruction, so then it executes this, which is to jump to where? To here, to 5024. So it jumps to 5024 and it fetches this instruction right there, this four bytes. And when it does that, it automatically increments the PC by 4. Because notice, after this one is fetched right there, the next instruction will be right there. Each one's 4 bytes. And the next one after that will be right here. And the next one after that will be right here, like that, okay? So every time it fetches an instruction, it increments the PC. So then it fetches the instruction at 5024 right here, gets that instruction. It looks at the first byte, the instruction specifier, decodes it, figures out what to do, executes, does it, then it looks to the PC, and now it says go to 5028. Goes to 5028 and fetches this instruction. And so immediately then, all sort of simultaneously, it increments by 4 to 5032. Now it's at 5028 right now. It decodes that instruction. And, here it is, the code here, declare a variable, see out inner number, all that. So it does that. And then when it's finished with that at 5028, it's done, it executed, it looks at the PC, and now it says go to 5032, goes to 5032, gets that instruction right there, but it increments the PC to 5036. So now it's 36. And so it finishes up with 5032, this right in here, does that. And then it looks at the PC, go to 5036, goes to 5036. When it loads this one in, that's the end of the function, but it still goes ahead and puts, that's the next address. It puts 504 here, 5040. That's not really that's not going to be the next instruction, but that's all it knows at this particular moment. It gets this instruction, so it adds 4 to 5036, and that's 5040. But when it decodes this instruction, it's the final curly brace or the return num. It's this part right. It's the end of the function. Go back to main. So it's not going to do 5040. It tells it where to go. And where does it go? Well, when it's the end of the function, the value that's been placed on the runtime stack is automatically, simultaneously, hardware, it copies it just electronically right into the PC. Okay, and then it's popped off the stack. It's gone forever. See, so it saved it, and when it got to the end of the function down here, right here, when it finished, did this last one, it's basically saying function's done, go back to main. Automatically, the CPU just fetches the next instruction. And where's the next instruction? 5004. Where's that? Right here. Remember, it started with this, and it did that. And that said, jump down to 5024, and it did those things in sequence. But when it got to the end, it automatically put 5004 back in the PC. So the PC always holds the memory address of the next instruction to be fetched. So now it's back to here. We won't go any further. It's the same routine. When there's another function call here, let's say it's right here. It goes to, let's say this is 5008. So it fetches this instruction. So as soon as it brings that instruction into the IR register, instruction register, it increments this to 5012, 5012, right? And so that's what's in the PC. It does this instruction here. It decodes it and executes it. And when it decodes it, it goes, it's function call, jump to calc result. And it tells it to put in the starting address. That's all done behind the scenes. We don't care. This is calc result in blue here. So it puts 5040 in the PC. It has to be in the PC, the next instruction that it's going to do. So the CPU goes, okay, got it. It's a function call. So it goes to the PC and gets that address, which tells it to jump down to 5040 and get the first instruction in this calc result function, like calculate the result. When it does that, it increments from 5040 to 5044. So when it finishes the first instruction, it goes to the PC, gets 5044, which tells it to go right here and get this instruction, and so forth. Keeps going. When he gets to the end, when he gets this last instruction right, where's it at? Here? Yeah. When he gets the last instruction, fetches it, it puts it's at 5052. It puts 5056 in the PC. 5056 in the PC, but it's still at this right here. It's at 5052. It fetches this instruction. It decodes it, and when it decodes it, decode means it figures out what to do. It's basically says into function, go back to main. So it also then immediately gets rid of this. Oh, by the way, when this started here, 5040, this first instruction, well, yeah, when it jumped to here, right, I'm sorry, you guys, it gets this instruction right here. It put this in the PC. So, excuse me, on the runtime stack, sorry, spacing out here. Bear with me. So what was that, 5012? So it puts 5012 on the stack to save it for later. That's right here. When it gets this instruction right here, which is to jump to this function, it saves this because when it comes back to main, this is what it will do next. See, it's doing it in order. It does that, then that, then that, then that. But every time there's a function call, like right here's a function call, it's going to do this right here. It's going to do this one, but not immediately following. It's going to do this, which tells it to jump down to and do this function here. But when it gets to the end down here, it's got to go back to main and continue where it left off, which is right after this, which is this right here, 5012. So it saves it on the stack. And so when it goes down here and it finishes up this last one, 5056, right? When it gets to, well, when it finishes this one, it doesn't do 5056, even though that's what's in the PC for just a brief nanosecond or two. Instead, it says, go back to main, function's done. So it copies the address in the runtime stack right here. It overwrites this, and it's 5012. So now it's returned back to main because 5012 is the next instruction after the function call. But it did jump down to the function. See, as human beings, we can go, okay, here's the function call. And okay, I got it. It's even in blue. I can see it real clearly. And it's going to do all of this. And then, oh, it's got to go back to main. Well, let me just, I can find it. Yeah, here's the function call. Yeah, it's got to be this one right here. See, but the CPU has no eyes. Everything is done electronically. So if it's going to do one instruction, it always does everything sequentially, unless there's a function call, in which case it's going to jump out of sequence down to some other code, but it has to return back to the next instruction below where it left off. So if this is a function call, this will be the next one when it comes back. Here's a function call. That's this code right here. Then this will be the address when it comes back. So before it leaves and jumps to the function, it stores this address on the stack. It did it here. Here's a function call. It puts that one on the stack. Jumps to get none. When it comes back, the one on the stack is put right into the PC. Put right into the PC. It takes it from the stack, puts it into the PC. It's all done by hardware, just electricity flowing. There's no software, there's no interpretation. It's done in nanoseconds. It's just the speed of electricity. So your program just processes things, jumps down to a function, goes back, but as soon as it goes back, it's immediately copied in from the stack that, that's where it was saved. Okay. So but every time it's fetched, like it goes to 5000 and it fetches this instruction, it puts it into the IR register, instruction register, and that's where it's decoded and executed. Okay, that's where it's decoded, and then after it's decoded, it goes to something called the arithmetic and logic unit, which we won't study. Arithmetic and logic unit is some circuitry in the processor that will do like adding and subtracting, comparing, shifting the bits, stuff like that. That's done in the ALU, arithmetic and logic unit. So now going back to our notes. So a couple of people added fairly quickly. We're barely getting started here. I just kind of went through these registers, part of the CPU. And so now remember, the accumulator and index registers are just general purpose registers where we can put a value in there and then add another value to it or whatever, or shift the bits or whatever. Program counter, though, is a very specific, unique register. It always holds the memory address of the next instruction to be fetched by the CPU. So we don't, it's off limits to us. We can't really, as a programmer doing assembly language, we can't move something to the PC register because that would screw the whole program up. It's got to always keep track of the next instruction. And the stack pointer is the same idea. We've talked about the runtime stack, how things are saved on the stack. And so the stack pointer holds the memory address of the top of the stack. Things are placed on the top, the top, and then they're taken off the top, okay? And so the stack pointer always holds the memory address of the top of the stack. So those two are kind of off limits to us. The stack, we'll find out later, stack pointer, we can actually write code to manipulate the stack pointer, but we'll talk about that later. And then the instruction register, we've already talked about the IR. It's where when the CPU looks to the program counter, PC register, to see where the next instruction is. And then it sends a signal to RAM to get that instruction at that memory location, puts it on the bus, brings it in, and puts it into the IR register. So they work together. PC says where to go get it, CPU gets it, puts it in the IR, and then it executes the instruction in the IR register is the one that's currently being executed, okay? And when it's done, CPU looks at the PC again to get the next instruction. So the CPU, when it does a fetch, it has to increment the PC, add to it each time. With the program we were looking at there, it was a 32-bit program, so it started at 5,000, and then it was incremented. When it got that, the address went to 5004 in the PC. We're using Pep8, which is 16 bits, a 16-bit computer. So if it fetches an instruction at 5,000, it would increment. Well, it depends on the size of the instruction. There's 1 byte instructions and 3 byte instructions. So if it fetches a 1 byte instruction, the PC increments by 1. If it fetches 3 bytes, the instruction is actually 24 bits, then the PC increments by 3. So if it fetches at 5,000 and it's a 1 byte instruction, then the PC is incremented to 5001. If it's a 3 byte instruction, it goes to 5,000 and gets 3 bytes, then the PC increments to 5003. So that's a little odd. There's 2 different things, either 1 byte or 3 bytes. But that's how it works. The principles are still the same, though, as far as the PC and the IR. Okay, here's a brief description. Accumulator, a register which contains the result of math or logic operations. So we can put something in the accumulator register, and then we can add to it, or subtract, or whatever we want to do. Index register used to access elements of an array. It can also be used as a general purpose register. We could move something to the index and add something to it, but it has special functionality dealing with loops and arrays. And we'll learn about that later. Program counter used to access instructions. The PC holds the memory address of the next instruction to be fetched. Stack pointer used to access elements on the runtime stack. It holds the memory address of the top of the stack, the place where something could be placed. Instruction register holds an instruction after it has been fetched from memory. So the CPU looks at the PC, goes to say, go to 5,000, goes to 5,000, and it fetches in 3 byte instruction, puts it into the IR, and then the PC is incremented by 3. So the IR gets 3 bytes. See, notice here that the IR register, the author has done it, it's 24 bits, 3 bytes. And so the author has done it as 1 byte and then 2 bytes. Some instructions are only 1 byte, some instructions are 3 bytes. So if they are 1 byte instructions, it just puts it into there. If there's 3 byte instructions, then it uses all 3 bytes. If it just brings in 8 bits, though, it just puts them in that 8-bit register. Okay. Main memory. So now we're talking Pep8. We're going to get specific into the Pep8 processor, CPU. It's 16 bits. And so every memory address is 16 bits. This address right here, 000B and 000C, those are hex numbers that are addresses, right? So here's an address. I'm just going to make this up. That's 16-bit. That's a 16-bit address. So we know how to convert that to hex. We know that would be what, an E? And there's a 3. And there's a 5. And there's an F. 4 ones is an F. So every 4 bits is 1 hex digit. So a 16-bit address, that's a big number, right? I mean, you know, that's when you have a 1 over here to the left, that's a large number. You know, I don't know how much it is, but maybe 30,000 or something. But anyway, but this is what it is. This is what it is as a hex value. Because every hex digit is 4 bits, therefore 16 bits would be 4 digits, 4 hex digits. Right? So up here, that's a real small address, isn't it? 000B. Here's the address. There's the first 0, second 0, third 0, B. It's still okay. So it's always a 16-bit address. So when the word size is 16 bits, the addresses are 16 bits. All addresses are 16 bits. So 0 is not that. 0 is 16 bits. And then 1 is that. And so on and so on and so on until you get to the last one, which is that. Okay? And so how many addresses are there total? This I've got to do superscript. Hang on a second here, it's right here. Oops, that's not going to do it. There we go. There. So if there's 16 bits, then the number of total possibilities are 2 to the 16th power. 65,536. I think that's correct. That's the total number of memory addresses. Not a lot, is it? So, you know, back in the day, in the early 1990s, when it was 16-bit computers, RAM, the amount of RAM a person could have would be, you know, not a megabyte. That would be, you know, 65K, I guess you'd say, 65,000. Right, pretty small, huh? They would all be positive numbers, you know, with memory addresses that starts at 0. So what you'd have would be from 0 all the way to 65,535, right? Because 0 is one of them. See, there's a total of 65,536 numbers. That's 2 to the 16th power. So to go from 0 to 65,535, that's all the addresses you'd have. The addresses actually limit how much RAM you can have. You know, on older computers. On newer computers, of course, on a 32-bit computer, I'll do it like this. Here's a 32-bit computer. Then you've got, you know, 32-bit computer means the word size is 4 bytes. So you'd have 2 to the 32nd power. And I don't know exactly what that number is, but it's about 4.2 billion. Oops, I don't know why I'm doing caps. Okay. So you can see how things radically changed when it went from 16 bits to 32 bits. The amount of RAM you could have in the old days was really, really little, you know. And then when they went to 32 bits, now you got 4 gigabytes of RAM. And then when they went to 64-bit computers, now the word size is 64 bits. And I don't even know, it's off the charts. It's a huge number. So we no longer have a real problem with, you know, for typical for PCs, at least, we don't have a problem with memory anymore, RAM. But in the old days, many people, including myself, you know, we would go to a store and we'd buy more memory, more RAM, and install it ourselves. But there was a limit, you know. I can remember going there because I didn't know much about this kind of stuff, and I'd go in and say, I'd like to buy more memory. I'm out of memory. And they'd say, you can't have any more memory because there's no more addresses left. You're limited by how many addresses you have, because every cell in memory is 1 byte, and it has to have a unique address. You can't have 2 cells that have the same address. You know, everyone's got to be unique. Anyway. Anyway, so that's the idea. We'll move on past it, but that's a Pep8 computer then. Oh, 535. Actually, 536. 535 would be the highest. It'd be an even number, right? 2 to anything would be an even number. It's 536. That's a goof on my part. Anyway, it doesn't matter. 65,000. Word size, Pep8 is 2 bytes. So all addresses are 2 bytes. All right, so now we're gonna get into the instruction set for the Pep8 CPU, for the processor. Every CPU, let's see, where are we at here? Hang on 1 second here. Page 2. Okay, going back up to here. The CPU fetches an instruction from memory, brings an instruction in across the bus and puts it into the IR register. And then it has to decode the instruction. Now this is Pep8, it's 16-bit instructions. So let's say that this is the instruction. That's 1 byte. I'll put a space just to separate things, but there wouldn't be a space. But okay, so here's an instruction. Now remember, each memory location can only hold 8 bits, 1 byte. So with Pep8, it's going to store it like that. It's going to store, let me do it like this. It's going to store the high byte first. Where was it? Right there. Here's the actual instruction, 16-bit instruction, right? Oops, okay, instruction. But when it stores it in RAM, it has to break it up into bite-sized chunks. So it stores the high byte, that's this one right here, first. That's this one right here. Okay? This is called Big Endian notation. We did discuss that briefly. I don't know if it's called formation or whatever, notation or whatever. I'll just call it Big Endian. So with Big Endian, the big end, the big end is stored first. That's unusual for PCs, by the way. That's the way the author has done it, and it doesn't matter. That's fine. It doesn't really matter. A lot of servers and large computers, server computers, use Big Endian. But generally, and you could Google it and look it up. So that's Big Endian. So now what I'm going to do then is copy this. And now we'll do Little Endian. So now with Little Endian, the little end, oops, I don't do that. The little end is stored first. So there's just 2 different ways. And it's hardware. It's actually built that way, the hardware of the computer, not software, the hardware. This is how most PCs are, Little Endian, and most servers, or many servers, I don't know about most. Yeah, I think even most probably are Big Endian. And there are some reasons, but we won't get into it. You could Google it if you want to get a little more information on it. You wouldn't need it for this class, but you might want to just on your own. Okay. So Pep8 computer though is Big Endian. That's just, it's important to know that because you have to know how it's stored in RAM and so forth. So this is Pep8. Here's a 16-bit instruction, because instructions are all instructions are actually instructions are either 1 byte or 3 bytes. Let's look at a 3-byte instruction. I should stick to here. Where is it at? Right there. Yeah. All right, we'll do it like this. So if it's Big Endian, then this byte would be stored lastly, so to speak. right here. Okay, so that's correct. So here's a Pep8 24-bit instruction. I said the computer's a 16-bit computer, but for whatever reason, the author has made them either 1 byte or 3 byte instructions. Okay, as I mentioned before. So this is a 3 byte instruction, and that's how it would be stored. CPU goes to RAM, so to speak, sends a signal out, go into some memory location, get this, and load it into the IR register. I'm going to go back to where I was here. Not sure why I did that. Oh, my point all of that was that when the CPU fetches an instruction, it fetches this instruction and puts it into the IR register. Here's the IR. Whoops, I'll have to move this down a little bit. It kind of got whacked out. So here's the IR register, and it's a 3 byte instruction. So this right here these 3 bytes are going to get loaded into the IR. This one first, and then these two down below. Okay. And then so it does a fetch, then decode, then execute. That's the cycle. Fetch, decode, execute over and over and over again. So now when it does the decode means it has to figure out what's it supposed to do. Well, there's no I don't know about humans how we think, but we might have intuition. CPU does not. The CPU, everything is just logic and just circuitry. So in other words, when it looks to decode it, it looks at the instruction specifier. This is the first byte is called the instruction specifier. Okay, that's the first byte. And it has to decode what this all means, all 24 bits. What is it? What is it? And the instruction specifier tells it what it is. And so this right here is an instruction. I mean, it's the instruction. It specifies the instruction. It's the instruction specifier. It might say add to the accumulator or move a value into the index register, something like that. Move something to a register, add something, compare something, subtract something, shift the bits left, whatever. It'll all be in this right here, in the instruction specifier. It tells it that. Okay, this right here. Oh, so the point is this: there's 8 bits that tells it what to do. That it specifies what the instruction does. So 2 to the 8th power, right? 2 to the 8th power is 256. So if the instruction specifier is only 8 bits, and with Pep8 that's all it is, then I won't bother to write 2 to the 8th power. It'd be 2 to raised to a power of 8, which is 256. So there are only 256 possible instructions in the Pep8 computer. As it turns out, the author's only, I think we have 39 or something, but this would be the total if the author wanted to make 256 instructions. But the author's trying to keep it simple. Just give us the basic stuff and teach us how this works. So there's, but see, 1 byte, there's only 256 different ways that you can rearrange, and then you get duplicates after that. So if it's an 8-bit instruction specifier, the author had to make up, well, in our case, only 39. He could have made up to 256, but he's made these instructions so that when this gets loaded into the IR down here, then the CPU looks at this, and that's the instruction specifier. It can then look in its list and go, no, that's not it. No, that's not it. No, 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 no. Ah, found it. And it will be an exact match. In other words, every CPU has a set of instructions. In the case of an modern Intel processor, heck was there? God, I used to know this stuff. I think there can be over 1,000 instructions in an Intel processor for a Windows operating system. There are some servers that have less instructions. There are some servers. This is not going to be something I test you on, but just to let you know, RISC computers are reduced instruction set. I don't know. I think it might be set. Computer? I don't know. Reduced instruction set. RISC. Some RISC computers, in other words, the set of instructions is reduced down. And so a RISC computer might have 300 instructions. Whereas an Intel processor to be used for Microsoft Windows might have 1,000 instructions. So at first glance, you think, well, that's not very good. The other one's got 1,000. But the more instructions there are, the more processing time. It takes just more time. The CPU has to process more things. There's more things going on. So servers and more powerful computers used for weather forecasting or robotics and so oftentimes they use a RISC computer because they don't want it to be able to show videos. They don't want it to be able to let people play games. They want to limit it down so it's a very specialized processor that will calculate numbers in the zillions for weather forecasting and do it very quickly. So they reduce the set of instructions, which makes it so it can process more quickly. Okay, but in the case, so I'm just trying to give you a little sort of an overview that a Windows operating system, an Intel processor might have 1,000 instructions. Because think about it, when you use your computer, you can play games, you can go on the web, you can listen to music, you can not just on the web, but I mean you could have iTunes or something and listen to music. It'll do a calculator. It'll let you use Microsoft Word. It'll let you use Adobe Photoshop, and and on and on. So there's a lot of instructions to be able to do all these different things. So anywhere from 300 to 1,100, and actually, for that matter, there are some many CPUs that might only have 20 instructions. If it's a robot that's on the assembly line for an automobile company where it does the same thing over and over again, gets something, twists, comes back, gets something, twists, there might be 20 instructions or something, or less. I don't know. So it just depends on what the processor is being used for. But every processor has an instruction set. Okay. And so when it fetches an instruction into the IO register, it looks at the instruction specifier. Now, if it's an Intel processor, for a PC computer, then this wouldn't be enough, would it? Because that would only be 256 instructions. If it's going to do 1,000 instructions, it would need to be more than 8 bits. It might, and I'm not sure if it can look at partial. In other words, to do 1,000 would actually require 2 to the 10th is 1,024. So it might take 10 or 11 bits or 12 bits, to say 12 bits would be enough to handle all the, each one being a unique 12-bit instruction. It might take 12 bits out of say 64 bits. Anyway, hopefully I'm not confusing you. So it fetches the instruction to the IR, looks at the instruction specifier to see what the instruction is. It gets that. It looks through its list of instructions. Pep8 only has 39. It starts at the first one. No, until it finds it. And then it executes. It fetches, it decodes, it executes. When it finds it, the electricity just flows and it does it. When it's done, it fetches the next instruction. It looks into the PC register because that holds the address of the next one, sends a signal to RAM, gets the instruction, brings it into the IO register, looks at the instruction specifier, which is the first byte there, decodes it, executes it, looks back to the program counter again, because that's been incremented to the next memory address, fetches, puts it into the IR, decodes it, executes it, looks back to the PC again for the next instruction, fetches, decode, executes it, PC's incremented, looks back to the, like that, keeps going. It's doing it. It's all hardware. There's no moving parts, just electricity, circuitry. So here are the instructions. Let me shrink that down. Here are the instructions. And so this is the instruction. It says instruction specifier. So now these are the instructions. These are the instructions. This is the binary instruction, 1 byte. They're all 1 byte here. The instruction, remember, the instruction can be 3 bytes or 1 byte, but there's always, the first byte is always the instruction specifier. So some, like this right here, that means program's done, stop. It's a 1 byte instruction. It doesn't need 2 more bytes to tell it to stop. So 8 zeros means stop, program's done. Okay. And we're not going to discuss trap until late in the semester, if at all. So if it says something about trap, there's only a few of them, but we won't worry about that. This one says move stack pointer to the accumulator. Remember that we have a register called the stack pointer, and we have a register called the accumulator. Let's go back up to that. Whoops, it was the other direction, wasn't it? Where was it? Well, I already went past it. Hang on, there it is. So here's the stack pointer. Here's the accumulator. So that instruction said move whatever's in the stack pointer to the accumulator. So if the stack pointer has, it's 16, these are all 16 bits. If the stack pointer has 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. If that's what's in the stack pointer, it's going to copy that. It won't take it out of the stack pointer, just copy it and put that, duplicate it into the accumulator. I don't know why you'd want to, but that's what it would do. Okay. So that's what that instruction was. Whoops. Oh, I see. It was just barely above it. So that's move stack pointer to the accumulator. Whatever's in the stack pointer, copy. They're both 16-bit registers. Just copy that and put it in the accumulator. Move the flags to the accumulator. So whatever's in whatever these are right here, it would put it in the low 4 bits. It put it in these first 4 bits on the right. Okay, that's what that would do. Branch unconditional. What this is, what a branch is it's, you know how oops, come on, Dennis, let's see, where should I go to here? Okay, with a branch, how should I do it? Yeah, okay, yeah. Hold on 1 second here. Just got to pull that one back up that I had before. What happened to it? No, it was not that one. This is this one is the one we looked at a few minutes ago. So when the PC has 5,000 in it, and it fetches that instruction, so it puts 5004 in the PC, and it puts this in the IR register, and then it looks at the instruction specifier, and it says, go to this function code, get num, which is down here, starting at location 5024. So it's got to put 5024 in here. So it saves this. We've already gone through this, but just briefly here. It saves it on the stack, 5024. And so what it's done here, it has jumped from doing this, instead of doing this next, and this in order, in sequence, it's jumped from here, from 5,000 to 5,003. It's jumped from there to 5024 right here, and now it's going to do that. And then when it gets to the end of the function here, it's going to jump back up to here, and that's what a branch instruction is. A branch instruction branch, sometimes in assembly language, they call it jump, but branch means do this and do this one next, or maybe do this and skip that one and jump down to some other place. I'll give you a good example. You'll be able to relate to this in C++ if we do something like this. If number is greater than 10, oops, okay. See out something, we don't care what it is. Okay, so if it's true, if number is greater than 10, do that. But if it's not, do that. If it's not, do this. Oops, not that. Okay. And so it's either going to do this or it's going to do this. Now in RAM, in memory, in the program, okay, I'm just going to take this right here. But this right here, pretend like it gets that this is, forget this stuff. So this if else, whoops, is going to be translated, it gets compiled into machine language. Whoops, it gets compiled into machine language right here. So this right here is this right here. Okay, so if this is true, that's, maybe we'll say, pretend like that's this instruction right here. It's doing a comparison. And then if that's true, do that. That's this right here. But if it's not true, do this. And we'll say that's right here. So 5,000 is loaded into the PC. Pretend like it is. And that says, go to here and do this. And what is that? That's this, compare. By the way, there'd be more instructions in this. I'm doing it real simply here. So this is basically doing this part, the if, okay? And if that's true, if this is true right here, then do this, which is fine, because when it does that right there, then it's at 5,000. It's going to increment the PC to 5,004, right? And so then is that true? Yes, it is. Then it simply does that. That's the next instruction. But then there would have to be, actually, what, this would have to be a branch instruction. So let me move this one down one to here. Okay, so if this is true, do this. And then right here, the next instruction would be branch to, this is not how you'd write it, but you just use BR, but branch to 5016. And that would be right. I'll take these two here. I'll just copy them. So this would be 516, 7, 8, and 9. Okay, so this is actually an instruction that in the whole instruction just says jump to here. So what that's going to do is it's going to skip this, isn't it? It's going to jump to here, which is whatever comes next in your program. See how that works? It's saying if this is true, then do that. And that'll be, if this is true, do that. And after it does that, it's going to jump. The next instruction says jump down to here. So it skipped that, didn't it? It branched around it. Sometimes they call it a jump. But let's say this is false. If that's false, then how shall I do that? If that's false, then technically we have to have it. It has to be right here. Oops, I went too far. Well, I I think hopefully you guys are getting it. So this would have to be I won't change the numbers. Oops. This would have to be a branch instruction. If this is false, it would branch around, wouldn't do that. It would branch to here and do that. Or wait, I'm getting myself confused. I won't go any further. The point is, things go in sequence. And with an if else, if it's true, it does the code right below it. But if it's not true, it's not going to do that code. It can't do that code. That's if it's true. If it's false, it needs to branch around it and do that. Okay, so there has to be a branch instruction right there. And likewise, if it's true, it will do the code right below it. But then after it's done that, the else is right there. So it needs to, after it does the true part, it has to branch around the false part. One way, it's got to skip around code, so it doesn't do both. Otherwise, it would do both the true and the false. That's a branch instruction. Okay. And we'll definitely be using branch. Generally, when we do MASM, we will be doing they're called jump instructions, and usually it's like this. You might have ones jump. Could be like jump on 0, and what that would be like. This is the 0. This is the 0 flag. If the 0 flag is set, jump. If the 0 flag has a 1 in it, then jump, and you have to put the address here. You have to have the address. Jump to some place. Anyway, enough of that. So okay, so that's I'm just kind of giving you that's what these branch instructions are. So it gives you just a very minor introduction to those. Many of these instructions we will not use in this class. We don't have enough time for it. But some of them we will. Several of them we will. And we'll talk about them. Here's arithmetic shift left. So so if this is the instruction specifier, remember it fetches an instruction, fetches an instruction, and it can be 3 bits or 1 bit. And it looks at the instruction specifier, the first byte. I don't know what I just said, 3 bytes or 1 byte. In fact, it looks at the first byte, that's the instructions, which will specify what it is. And so it looks down here and I'll go to that arithmetic shift left right here. And so there's the instruction specifier. Now I haven't talked about R bits and A bits or 3 A bits. So let's take a look at the instruction, the arithmetic shift left. For example, here it is right here. So okay, 0, 10, and 3. Okay, here it is. What did I just say? Oh, I've already screwed it up. That can't be right. Doggone it. Oh, maybe it was 0. Okay, I forgot already. Where's it at here? Here it is. So okay, 0, 4 1s, 3, 3, 0. Okay. Hopefully I did that right. Arithmetic shift left. So if this right here, that's 1 byte. The R bit is 1 bit. But let's take a look at this. So this is basically this. So ASL. So let's do this. Let's look up the instruction to load into the accumulator 1 word. That's 16 bits. Remember, Pep8 is 16 bits. The word size is 16 bits. So load into register R from memory 1 word into a register. Here it is. So remember, an instruction can be 24 bits, 3 bytes, or it can just be 1 byte. If it's a stop instruction, there's nothing confusing about this. 0 means stop. Program's over. It's like return 0 in C++ or something. It just means it's done. Okay. But if we have something like this, the R bit, if you notice down here after the instructions, it gives us a little description of what the R bit is. If it's a 0, it means it's the accumulator. If it's a 1, it means it's the index. Okay. So this right here, that's the load instruction. And it's saying load into a register. Okay, well, let's say, what if it's like this? 1 1 0 0. And now let's put a 0 right here. Right here. So that means 0 means it's the accumulator. Okay, register. Okay, if this is a 1, it means it's the index register. But it's the accumulator. We only have 2 registers that we can move something to, index and accumulator. Remember I mentioned that the stack pointer and the flags register and the IR, those are off limits for us. So if you look down here after the instructions, see there's only 2 possibilities. We can only use 2 registers. In a when we start doing assembly language the second half of the semester, then there are more than 2 registers that we can use. Let's see, we started at 3. We should take a break, you guys, because we still have a ways to go. I wanted to stop a little sooner. So I'll tell you what, let's say 442, 452, 457. We'll start at 457, which is kind of a random number. And I'll tell you what, I'll just go for 4 more minutes till, so it's 445. Then we'll stop. So here we are. So the first instruction is this instruction right here. And so what do we have? We have load into a register. What register? The accumulator. And now we have 3, they're called addressing modes. So what are we going to load into the accumulator? Remember, the instructions can be 1 byte or 3 bytes. They have to be 1 byte or 3 bytes, nothing else. 1 byte or 3 bytes. Okay. So we're going to load something into the accumulator. Well, we can't, in other words, if we just went like this, or something, that's not enough. I mean, that's nothing. You can't load, that'd be a 7, I guess, if you want to do it like that. In other words, this is saying load into the accumulator, and we're going to have to use three bytes. I'm going to leave these 3 A's here for a second. And now I'm going to give you the second, the other 2 bytes. I'm going to make it a real small number. There's 1 byte. So that's a 3, isn't it? That's a 3 right here. That's a 3. It's because there's a 3. 16 bits is a 3. So now this is saying load into the accumulator this. But what is this? Oops. I'm stuck on it. There we go. So the compiler or the CPU has no clue what that is. Is that a 3 or is that a memory location 3? If it's a memory address, it would be saying move into the, 1 word, 16 bits, move into the accumulator, whatever is at this memory address, right? Or it might be saying move into the accumulator this value, this actual value, okay? And that's what this right here tells the CPU what this is. It's called the addressing mode. So now let's look at down here. It'll show us. The addressing mode, if it's a single A, it means immediate. And that's immediate means an actual value. If there's 3 A's and they're all zeros, that means an actual value, immediate. So if we go back up to here, and we put 3 zeros right here, then let me move this down here. So what do we have? The R equals 0, which means accumulator. Oops, not a capital R. And then 3A bits right here. Whoops. Equals. See, that's these three, right? That's the, here, I'll do it like that. And the R bit. There you go. So the instruction specifier is that right there. And it's made up of what's called the opcode, operation code, plus the R bit and 3A bits. So now let's take a look at it. What do we have here? And remember, 3 zeros means immediate, a value. Turn this back into black again. So, well, no, I'm going to end up going past time, isn't it? Let's stop right there. This we'll pick it up. So it's a 4:45. We'll start right at 5 o'clock. So I'm going to stop the okay, we're recording again then. So here is an instruction, 24-bit. Remember, Pep8 is either 8 bits or 24 bits. So it fetches the instruction into the IR. It looks at the instruction specifier, that's the first byte. And here's the instruction. Here's the instruction specifier. 1100 and 4 more zeros. Okay. And so then it looks in its instruction set and it finds this right here. And if the R is a 0, it's accumulator. If it's a 1, it's the index register. And it's the accumulator. So now it says move 1 word, 2 bytes, into the accumulator. And then here's what it's moving. But that could be one of a couple of things. It could be an actual value, or it could be a memory location. It's a 3. So this tells it what it is. And so that's immediate, 3 zeros or 1 0, either way. 3 zeros means immediate addressing mode. And immediate means an actual value. So it's saying this value right here, which is a 3, move that into the accumulator. That's what this whole thing says is move a 3, an actual value 3, into the accumulator. Now, going back down to here, if we look at the addressing modes again, sometimes the immediate is only 1 0. So if we go back up to here, let's find one here. Like these are all one. These are all I'll say it, one addressing mode bit, 1 bit the addressing mode instead of 3. So it's 1 or 3. So if we just do something like this right here. Guess I'll just move that down a little bit. So this is a branch unconditional. And so that's just the instruction specifier. But if we look at it more closely, we'd have 1, 2, 3, 4, 5, 6, 7, 8. Okay, so now in this case, the A bit is 0. And that's immediate, right? 1A, oops, this shouldn't be capital. It doesn't matter if it is. So that means immediate, which means an actual value. I'm not even sure how that would work. Well, I won't get into that. Let's change this. Let's take a look. Let me go back down to here again, because branch is kind of a weird one to do it to. But let's say, see, it's only a 1. Yeah, I picked a bad choice. Let me pick something different here. Bad examples. Yeah, that's a bad example to use. gets too carried away. Pass on this one for the time being. Anyway, immediate can be either 1A or 1 0 or 3 zeros. Okay, let's just leave it at that for now. But if we go 0 0 1, then it means that it's called direct addressing mode, which means that it's a memory address. Okay, so now let's go back to this again. Let's put in some bigger numbers. just so it looks kind of weird. Okay. Okay, so let's see. There's 5, 6, 7. There's 1 byte. Is that 1 byte? 1, 2, 4, 5, yeah. Okay, and here's the second byte, right? Yeah. Okay, 2 bytes. Okay, so now this is, and we're going to change this. We're going to change this to this, but we're going to change this to 0 1 0 0 1. So now here it is, as the addressing mode is 0 0 0, which means it's a value. Okay. This right here is an actual value. That'd be a big value, wouldn't it? Because that's the high bid. So this would be whatever that would be, 32,000 or something, half of 65,000 plus some extra. So so that's 34, 35,000, whatever, something like that, right? Or higher. Okay. And so this is saying move into the accumulator. And this is saying this is a real value right here. So it's basically saying, like, move into the accumulator 35,000. Okay. But now we'll have the same instruction here, but we'll change this to a 1. So now it's saying move into the accumulator, direct addressing mode. That's this right here. 0 0 1 means direct addressing. So this is immediate. This is direct. If it's direct, it means that it's a memory address. So now it's saying move into the accumulator, whatever's at this memory address. Addresses are always 16 bits in Pep8. It's a 16-bit computer. So this is some memory address. I don't know what it is, but it's a memory address 32,000 something, blah, 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 whatever. Okay. So in other words, you can see this here, it's a memory address. So we'll go to that memory address and whatever's there. It might be a real small number. It might be a 5 in there. Move into the accumulator a 5. Okay. But this is saying go to that address. Here it's saying put this big value, put that in the accumulator. So immediate means a value. Direct addressing, I don't know why they call it. It's called direct addressing. Means that that this part is not a value. It's an actual memory address. And go to that memory address and get whatever's that value there. There's 8 addressing modes, but we're only going to look at 2. So there's the good news. If we go down to here, you might want to make a note of this. There might be some homework assignments that would have more than 2 addressing modes, but we're only going to discuss immediate, this right here. I don't know if I could do that. Maybe like this. Yeah. And that, of course, this is immediate also. And then direct. The others are all like if you use 0 1 0 or stack relative, these different things are indexed. They mean something. We just don't have enough time to study them. And so when you look at something like 0 0 0 means it's an actual value. 0 0 1 direct addressing means go to that memory address right there. Go to that address, and whatever's there, put it in the accumulator. But if it could be 0 1 0, I think that's indexing or indexed. And these other ones, they had to do with from a particular location, so many bytes to the next location, or so many bytes from the top of the stack. There's stack relative. There's different things, but we're not going to get into that for our class for right now. We just need to get the basic fundamentals of how the CPU looks at the instruction specifier and decodes it into what's called the opcode. The opcode is the actual stuff, part of the instruction specifier that doesn't have any R bits or A bits. That's the opcode. In this case, that's the opcode. If we just use let's just take a look at this. The opcode here. Well, first of all, the instruction specifier would be the whole byte, the first byte right here. That's the instruction specifier. And then this part of it is the opcode. So let's go to here. Which means move a word that's 2 bytes to a register. Okay, and then R bit. Let's put it over here. R equals 0. Right? Here's the R bit, it's 0. Here's the opcode. And there's 3 A bits. I could just say addressing mode, but that's all. I'll just do it like that. Oh, I guess I could have done it that way. So that's the addressing mode, 000, and that says that the operand specifier is an actual value. So what's the operand specifier? This right here. Okay. So this is kind of breaking. These are the proper terms. You'll need to know these for the for the midterm exam, but also you should know them. I mean, this is computer science, and so we have an instruction, and it's a 24-bit instruction, 3 bytes. If it was a bigger, 32-bit computer, then the instruction would probably be 32 bits. And if it's 64 bits, 64-bit instructions. But there's still going to be an instruction specifier and an operand specifier. And then within the instruction specifier, you can break that down further into the opcode, the R bit, and A bits. See, opcode would be, this actually says what it does. Move to the accumulator. And then, this actually, excuse me, this says move to a register. And then it takes the R bit to say what register? The accumulator. And move what? Move, what is this right here? This specifies what the operand specifier is. This is the operand specifier. And this says it's a real value, 34,327 or something like that. Okay. That's how it works. If we change this to 001, right? Like that. The opcode's the same, the R bit's the same, and now this is that. And so this would be direct addressing mode. And so now it'd be a memory address. And it's talking about, it's describing the operand specifier. It's saying the operand is a memory address, not a value. Okay, let's keep it real simple. Let's just say that the operand specifier is a 3. Okay, so if we do it like this, it would say move whatever's at address 3. It's a pretty small address. Move whatever's at address 3. Move that in the value at that location at address 3. Move that into the accumulator. If we change it back to a 0, then this is immediate. And now it's a value. And so now it's saying move this is a value now. Now it's a 3. Put a 3 into the accumulator. That's how it works. So that's what these do. These describe the addressing mode always just describes what the operand is. And, of course, the R bit says which if we change that to a 1, if this is a 1, now it's the index. I'll just use an X for index. Okay. So this is the opcode. So the opcode is it's the operation code or operational code. It's not the whole byte. The whole byte includes the opcode plus R bits plus there's only one R bit, by the way, and plus the A bits. There can only be one R bit because it's only going to do something with one register at a time. So it's going to be shift the bits left in the accumulator, shift the bits right in the index, but it can't shift them in 2 registers at the same time. Move something to the accumulator, move something to the index. So there's only one R bit, always, just one R bit. Okay. Okay. So this is how it shows up in the instruction set in Pep8, right? Where's it at here? Okay. Here it is right here. Load into a register from memory. It's one word. You can actually load 1 byte, by the way. To load a byte, well, let's take a look at that instruction. No, that's okay. See, it's still it just changes slightly. It has a 1 right there. So the opcode is this 1101 into some particular register. And then you specify what it is that you're loading. So let's do that. Like, let's say, for example, let's say we do something like this. There. So this, let me take that off of bold. Okay, so this would be 1101 R AAA. So then we can see then that the instruction specifier is 1101, which is okay, 1 byte, not 1 word, just 1 byte to a register. Okay, and then the R bit is the index register. And then the 3 A bits, oops, is, where am I at here? 3 zeros. Oops, not there. Come on. And so that means it's immediate. So this is specifying that the operand is an actual value. So then you would have something like well, in that case, it would load the low byte. In other words, let's just say you had something like this. Well, we'll make it real simple. There's 1 byte. There's a 3 again. So if the instruction is load a byte into the index register, and this operand specifier, the operand is a value. So this is a 3. So what it would do, it would take the low byte right here. Okay, I'll just do it like that. And it would load that into the low byte of the index register. Yeah, well, good. Here's the index. It would load it into the low 8 bits right here. It has the ability to do that. And when we do later on after the midterm, when we do start getting into assembly language, we can do the same thing. We don't have to move then we'll be working with a 32-bit MASM, a 32-bit processor. And so we'll write our assembly language code, and we have the ability to put it in all 32 bits, move a 32-bit number into a 32-bit register, or we can do half. We could say move a 16-bit value into the low 16 bits of a 32-bit register, or we could even say move just 8 bits into the 1 byte of the 32-bit register. Okay. So we have two ways that we can, we can in Pep8 we can load 2 byte, 1 word, 16 bits into a register, or we can just load half of it, just into the low byte. Anyway, that's kind of the idea there, and there's a bunch of other instructions here, and so we're only going to concentrate on this right here, and so it simplifies things. Then for the addressing mode simply says what the operand is. It's either going to be a real value, a 3, or it's a memory address, 3. That's pretty low. Okay. So, by the way, next class, we do Pep4B, and it's really a continuation. It was all the same lecture. I just divided it into 2, so we don't have to finish everything today, because next time, but then I've got the Pep8 quiz. What's it? Oh, it only covers 2 lecture. Oh, but you guys are asynchronous, so you can take it whenever you want. Okay, so never mind. So, but anyway, my point is that we'll continue with Pep lecture 4B, which is really just a continuation of lecture 4. Okay, let me see how we're doing here. Just want to make sure this stuff we'll be able to go through fairly quickly because we've done it. Yeah, okay. We'll go a little bit longer here then, because this is just a repeat then. So instruction format: each CPU has its own set of instructions. Pep8 has 39. An Intel processor has 1,000. A RISC computer has 200 or 300. Gives you perspective. So this is a real small computer, isn't it? Only 39 instructions, and we're only going to look at maybe 10 or 12 or 14 of them, just enough to be able to understand how the CPU gets the instruction, fetches it, and then decodes it, and then executes it. 2 types of instructions: 1 byte and 3 byte. Instruction specifier: every instruction begins with a 1 byte instruction specifier that specifies what the instruction does. The one we were looking at was 110. That was load 1 word into a register, and then this specifies what to load, what the operand is. But that was the whole thing was the instruction specifier, which is the opcode, the R bit, and the A bits. Opcode, operational code. Operation code specifies the operation consists of 4 to 8 bits. Let's look at that. Here's all of the instructions. So here's an opcode. The instruction specifier or the opcode, I'll put it that way. Well, the instruction specifier is also the opcode, right? There's no R bits and A bits for all of these right here. All 8 bits is just an opcode, and there's no operand. It's just, that's the whole instruction, 1 byte. Here's one that would be a 3 byte instruction. Whenever you have an A bit, an addressing mode bit, the A, it means that it's describing what the operand is. So there's going to be a 16-bit operand. So now this is the instruction specifier. The opcode would be 7 bits. That's the opcode. And no R bit and 1 A bit. If we go to here, we have an instruction specifier, 8 bits. The opcode is 7 bits and 1 R bit and no A bits. The reason why there's no A bits here, let's take the shift again, this one here. Here it is right here. So this is saying shift the bits in the register. So what register? It's the index. I mean the accumulator. No, it's the index. See? And so there's no operand. You're not saying move something, that's the operand, move something into a register. In this case, you're just saying you got the register right there, the accumulator, shift the bits. So there's nothing else. It's a simple instruction, isn't it? Just go to the accumulator and shift the bits to the left or shift the bits to the right. So there's no reason for an A bit. An A bit is when you have an operand, another 16-bit operand. Okay. And so on and so forth. So in any case, doesn't matter which one it is. The whole thing is the instruction specifier. That's the opcode, 4-bit opcode. 1 R bit, 3 A bits. So some of them some of them, come on, Dennis, are 4 bits for the opcode. Some are 5 bits. That's 5. Some are 6, probably somewhere. I don't see one 6. Doesn't matter. Who cares? Here's one that's 7, and then a few at the top. These are what we call unary instructions. Unary means there's no operand. It's just a 1-byte instruction. Just these 4. Those are the only unary instructions. Those are called unary instructions. Unary means just 1 byte. Okay. But most of the instructions, as you can see, as soon as you get starting into an actually, that's not true. Some of these would be too. When there's no A bit, like these right here, these would be unary, because it would just be, where's that shift again? Right here. This is just saying shift the bits in the accumulator or shift the bits in the index. So that's just 1 byte. Doesn't require any 2 more operand, 2 more bytes for an operand. Okay. So the opcode is 4 to 8 bits. Here's an example of an 8-bit opcode where the whole instruction specifier is the opcode. No R bits, no A bits. There's stuff about with an in bit. We probably won't do what it says here described later in the chapter, but I don't think we will. You're on your own for that. We just don't have enough time. So we'll leave that one alone. All right, and so here's just talking about an R bit. So what is it? Oh, this is negate register R. So that just means like if you have a 5 in the accumulator, negate that it's an instruction, it will make it a -5. Okay. If you have a -7, and you negate it, it makes a +7. Okay. That's what, and so it doesn't really, where am I at here? It doesn't really require an operand, does it? It's just saying whatever's in the index register, negate it. So it's just 1 byte. It's a 1-byte instruction. And the instruction specifier is 1 byte. The opcode is 7 bits. That's the opcode. And 1 R bit, no A bits. Okay. So here it says when R equals 0, then the accumulator, this is the accumulator. Here's the index. So this is saying negate whatever's in the accumulator. And you know how that would be in math or C++. If you have a 7, if you multiply it by -1, you've just negated it, right? And if you have a -5 and you multiply it times -1, you have a +5. So it's kind of the same idea. So this is just saying whatever's in the accumulator, make it negative or make it positive, negate it. And if it's in the index, if that's it, the R bit's 1, then whatever's in the index, negate that. And then okay, I just from experience, I found that we don't usually get around to doing the other one. So we're only going to be concerned with immediate and direct addressing mode. Whoops, I'm not even in the right spot here. Anyway, immediate, remember, immediate was actually single 0 or 3 zeros was immediate. We can look at that up here again real quickly. So if it's a single, if it's 1 A bit and it's a 0, it's immediate. We won't worry about index. We won't get involved in that. So immediate is a 0, or it could be 3 zeros. And then if it's 001, 3 A bits, 001, then the operand is a memory address. Just trying to drive that point home. Okay. Let's take a look at this one here. Here's an example. Determine the opcode register and addressing mode for this instruction. This is hex, right? Obviously. So we have to convert it to binary first if we want to be able to look at our instruction set. So we've already done this. C1 would be, there's a C and there's a 1. See how this is? That's a 3-byte instruction, isn't it? Remember, instructions are either 1 byte or 3 bytes. 8 bits or 24 bits. So C1 is that right there. So that would be the instruction specifier. right? Instruction specifier. And then 004A, remember every hex digit is 4 bits. So there's 1 byte. Oops, I keep getting confused. 00 is 1 byte, and then 4A is another byte. So there's 1 byte, that's 00, and here's 4A. Okay, so that's one total instruction. It's made up of the first byte is the instruction specifier, and the next 2 bytes is the operand specifier. And then the instruction specifier has an opcode, R bits, and A bits. So let's look at it. Here's the instruction specifier. Oh, and by the way, see, once you get it into this form right here, right like that, then you can look in the instruction set and see what the instruction is. So we're looking for 11000. Let's just go this far. It won't even be that far, but 11000. So let's go up here. And if we look through here, 11000, you can see it's not going to be any of these. It's going to be 11000. And so we get to here, 1100, and that's as far as we need to go because it's the only one that's 1100. So it's load register R, one word, excuse me, loads 1 word. This one I wasn't thinking about that at the time, but whatever, it is what it is. And so we just did that previously. Here it is. So you have to look at the instruction specifier to find out what the opcode is. And we found out that it's 1100, load one word into an accumulator. So there it is. So, okay. Once the opcode has been determined, 1100, the remaining bits of the first byte, these right here, the remaining bits of the first byte represent an R bit, if one exists, and in this case it does, and 3 A bits. So we have an R bit and 3 A bits. And then we have the operand, that's 004A. We already saw that up here. 004A, that's this right here. But the addressing mode is 001, and that's direct addressing mode. We can see that from right. Come on. Where's it at here? Right here. Direct addressing, which means the operand is a memory address. It's not a value. It's not a 7. It's a memory address, whatever that address is. Well, we know what it is. It's 004A. It's this, which is 004A. We saw that right here. That's the operand specifier. And what is it? It's a memory address. 004A is a memory address. Okay. And look up the value of the R bit. It's 0, which means it's the accumulator. The last 3 digits represents the addressing mode, 001, which means this is a memory address. So that means go to that memory address and get whatever the value is inside. It might be a 5, it might be 2000, whatever it is. At that address. This is just the address in RAM and whatever's there. Make a copy of that and put it into the accumulator. So I'll tell you, we'll stop here. I have the answers to, there's about 5 exercises. If you can, I recommend that you try them before our next class next week, and then it'll I think it would help you a lot as far as reaffirming whether you're getting it or not. So see what it's doing is saying here's an instruction. So it was determine the opcode register and addressing mode. So this is the complete instruction. Well, I wonder if I just did opcodes only. That's kind of surprising me. Yeah. Okay. These are just opcodes then. Oh, that was kind of lame. Okay. In other words, the reason why I know that is because we just did this one. 1100 was load 1 word into a register, load into the index. And then what's 011? Back up here to the addressing modes. We won't discuss what it is, but you can at least write it down. 011 was, what was it? This one? Stack relative.
It's a particular addressing mode relative to the position in the stack, but we're not going to get into it, but you could still write it down. Just look in there's 8 addressing modes. So there's 5 exercises here. Here's 3 of them. They're not complete instructions, though. They are only they are only the instruction specifier. And so you can determine the opcode by looking in, find this particular one in the instruction set, and then see what now which one's the R bit. It might be this one, could be, and then the addressing mode. So you just write those 3 things down. Okay. Tell you what, we'll do it as extra credit. There's not many people here. I guess if somebody watches it later in the week, they could still turn it in. We'll make a deadline though of next week. If you can get it in before I go over the answers, just email it to me. We'll make it extra credit. There's, I think, 5 of them. There's 3 right here, and there's 2 more down below. But they're really similar to what would be on a midterm exam. So I think it'd be good for you. So all you do is just take a look at that, and then go up into the. And by the way, the instruction set is it's in Canvas. It's right with the lecture. Well, it's actually part of the lecture. And by the way, the good news is, I guess the bad news is midterm is coming, but the good news is you don't have to memorize these instructions. For the midterm, you'll be given the instruction, so you can look at it, or you'll even have it at your home. You could have it so you can, because you can download the lecture notes, and you'll have the instruction set right there. So when you're doing if it's asking for an opcode, you can look on your list and find it, and then see what it is. Okay. So you don't have to memorize nor do you have to memorize, not that it's very hard, but you don't have to memorize that, or it's only going to be these things here, the immediate and indexed, immediate and direct. But all these instructions, 39 of them, you don't have to memorize those. Those will be on a sheet that will be available for you. So we'll stop right here. That's right where it gets into it'll say classroom exercise number 1, and it'll be a classroom exercise number 2 that follows this. I don't want to go any further because I got the answers there. And so we'll knock off there, and we'll continue right at this point here. Okay. Next class. Yeah, do it like that. And that's page 7, at least on my sheet here. Okay. All right, you guys, let me I'll just go ahead and stop the recording now.